Taking the derivative of a function is one of the most important things that you can learn in calculus. It is going to be the subject of this lecture. We shall need the concepts of limit and of continuity that we talked about earlier, but let me begin by reminding you of what the slope of a straight line means. Suppose I have 2 points, one over here, the other over here, and this is a distance delta x, and this is the distance delta y. Then the slope of the straight line that passes through these 2 points, which I'll call the slope or the gradient, is delta y divided by delta x. You see, what this delta y means is that this is a distance. It's a name for this distance over here, and delta x is a name for this distance over here. You cannot cancel the deltas over here. This is one full name, that's another full name. Here the slope is 0.69. So this is 1 unit from here to here, and this is 0.69 units from here to here. Let me change the slope of this straight line and let's see how it increases. So now the slope is 0.95. It's gone up to 1.23. The line has become steeper and steeper and steeper. Let me take it back in the other direction, and now it is heading towards becoming flat. When it becomes flat, the slope becomes 0. I can't make it exactly 0, unfortunately, but you see that it's now gone past and gotten negative, and now it's becoming more and more negative, and you see that it's becoming steeper in the other direction. Let me take any 2 points on this curve, one which is the yellow dot here, and the other which is the blue dot over here, connected by a straight line, the red line. Now let me move the yellow dot towards the blue dot. As it becomes closer and closer, it becomes what is called the tangent to the curve at the blue point. If the 2 points become closer and closer to each other, then there's no point in drawing them separately. So here I have just 1 point, and there is a tangent, that is the point that connects 2 very, very closely spaced points on the curve, and the slope of this tangent is 0.23, which means I go 1 unit in this direction and 0.23 in that direction. The tangent is at this point, and now I'm going to move that point around. You see that if I go upwards, or rather to the right, the slope becomes bigger. It's now 0.8, and it becomes still larger here. It becomes larger and larger as I move in that direction. If I move back, then you see the tangent is getting flatter. The slope is getting less. It's very close to 0 over here. And now if I move in the other direction, the slope has become negative. The line is now tilted the other way. And as I go up, the slope changes until it reaches the flat point at which the slope is very close to 0. And then again the slope starts increasing as I go to the left. Of course, pictures are very nice in explaining what a tangent is, but we need to have an algebraic definition of what the tangent is at a given point. So let's look at this definition. A function f of x is differentiable at the point x if the limit of f at the point x plus epsilon minus f at the point x divided by the distance between the 2 points, which is epsilon, exists. It's exactly what we've discussed earlier. Here is some curve. Here is the point x, and here is x plus epsilon. Epsilon is some small number which will keep getting smaller and smaller. So epsilon is the distance between here and here. At this point, the value of the function is f of x, and at this point, the value of the function is x plus epsilon. Of course, if epsilon was exactly 0, then you see on top, I would have f of x minus f of x, and at the bottom, I would have epsilon, which would be 0. And so this would be 0 over 0. And 0 over 0, as you know, means nothing. It's not defined. So it's very, very important that you remember that epsilon is some small number. Make it as small as you like. Make epsilon equal to 0.0000 and put 2000 zeros over here, and at the end put a 1, or put 1 million zeros and put a 1. You can make it smaller and smaller, but you cannot make it exactly 0. In that case, this limit gets denoted either as f prime x, and this is what I like to call it. So every function f has a derivative which is f prime x. Some people like to call it df by dx, which is fine. Others like to call it df by dx at the point x, which is also perfectly okay. But this notation over here is the one that is used in modern mathematics. Let us now work out a few examples of derivatives. The basic definition is written over here. And let's begin by taking a constant function. Now, of course, what that means is that f prime at the point x is going to be c minus c over epsilon, and that's 0 over epsilon. That's 0. It doesn't matter what epsilon is. We remember that epsilon is not 0, and so this is well defined. The derivative of a constant function is 0. Well, now let's take this straight line, f of x equals f cx plus d. Here, f prime of x is going to be c of x plus epsilon plus d minus c x minus d divided by epsilon. So the d's cancel, cx cancels, and this is just c into epsilon over epsilon, which is c. What we've learned is that the derivative of a linear function, that is to say one that has only one power of x, is a constant, and that constant is the thing that is multiplying x. So the answer is C. Now for a slightly more complicated example, the function f of x equals x squared. Here we need to find the limit of x plus epsilon squared minus x squared divided by epsilon. And now this is x squared plus 2 epsilon x plus epsilon squared minus x squared divided by epsilon. Notice that the x squared cancel, but here we have epsilon, epsilon, epsilon. Let's divide that out. So that gives us 2x plus epsilon. But since epsilon is going to 0, we can just forget about this. And so the result is that f prime of x is equal to 2x. The derivative of this function at the point x is 2x. Let's now work out a slightly more complicated example. Here we shall need the limit x plus epsilon to the power n minus x to the n divided by epsilon. And this, of course, is x plus epsilon into x plus epsilon and so forth all the way till x plus epsilon the nth time minus x to the n divided by epsilon. Now let's look at the number of times that x occurs alone. That's n x's multiplied together. So we have x to the power n. That comes from this, and all the x's in between. If we look at the number of times that x to the power n minus 1 occurs, that happens with an epsilon. And that is n times epsilon x to the n minus 1. And we've got to subtract off this as well. I'm going to neglect all the powers of epsilon squared and epsilon cubed and so forth. So I'm going to call that order of epsilon squared. These are things that can be neglected. Why? Because epsilon into epsilon is much, much smaller than epsilon, obviously. And so, doing this little calculation over here, we see that this and this cancel, epsilon and epsilon here cancel, and we get n times x to the n minus 1. And so what we've proved is that f prime of x is n times x to the n minus 1. Let's now work out this example. F of x is square root of x. In this case, we need x plus epsilon to the power half minus x to the power half divided by epsilon. And now there's a little trick we can use. We can multiply by 1, but let me write this as before. And what I'm going to do is multiply by x plus epsilon to the power half plus x to the power half divided by the same thing. So x plus epsilon to the power half plus x to the power half. That is just 1 over here. And now let's note that this is like a minus b into a plus b, which means that we're going to get a squared minus b squared. In other words, x plus epsilon minus x, and at the bottom there is epsilon into x plus epsilon to the half, but epsilon is very, very small compared to x. I'm assuming x is not 0 over here. So we can neglect this epsilon compared to this x over here. And so we get at the bottom 2x to the power half. If we subtract off this x with this x, then we get the result 1 over 2x to the power half. Or in other words, 2 square root of x. That is the derivative of f of x equals square root of x. But let's plot this and see what it looks like. We just derived this result for the function f of x equals x to the power half, that f prime of x was 1 over 2x to the power half. Now, here is a plot of f of x. So this is f of x. Now notice that as x becomes smaller and smaller, the derivative over here, f prime of x, is getting larger and larger. And you can see that here is the derivative at this point. At this point, at close to 0, the derivative is approaching infinity. And so therefore, what we've derived algebraically and what we plot over here are very much the same. If you look at negative values of x, then of course you would get the square root of minus x. So what I have over here is actually f of x equals square root of magnitude of x. And that is an even function. It's the same on both sides. You can see that as you approach from the left, the slope is getting lesser and lesser, but it's becoming steeper and steeper. And so eventually this derivative will go to infinity, but it'll go to infinity in the downward direction. We also need to take the derivative of the sine function. Here we need the limit of sine of x plus epsilon minus sine of x divided by epsilon. And now I'm going to use a trigonometric identity. You've seen this in the form before, that sine of a plus b is sine of a cosine of b plus cosine of a sine of b. And now let's use this to write this as sine x cosine epsilon plus cosine x sine epsilon minus, of course, sine x, and we've got to divide by epsilon. Now, recall the following, that as epsilon becomes very, very small, cosine of epsilon goes to 1 minus epsilon squared by 2. We derived this in the last lecture, and we also derived that sine of epsilon goes to epsilon. Okay, so let's put that up over here. And so the result is that we're going to get sine x multiplying 1 minus epsilon squared over 2 and cosine x multiplying epsilon and then minus sine x and divide by epsilon. Now this sine x cancels with this sine x. Epsilon squared can be neglected compared to epsilon, and so we get cosine of x into epsilon over epsilon, and that's cosine of x. Therefore, the derivative of sine of x is cosine of x. What about cosine of x? Well, we'll do this very similarly. Here we need cosine of x plus epsilon minus cosine of x divided by epsilon. And again, we can use cosine of a plus b. You know what that identity is. I will just write it out over here. Cosine x, cosine epsilon minus sine x, sine epsilon divided by epsilon. And we've got to subtract off, of course, the cosine x, the one that's over here. Well, as epsilon goes to 0, cosine of epsilon goes to 1 minus epsilon squared over 2, as is above over here. We're going to neglect the epsilon squared again in comparison with epsilon. And so we get cosine x, cancelling this, minus sine x. And now this sine epsilon is to be replaced by epsilon. And so this cancels that. We divide by epsilon. And the result is minus sine x. This is a very important result, that the derivative of sine x is plus cosine x. The derivative of cosine x is minus sine x. Derivatives are very commonly encountered in daily life. Consider a particle that's moving, let's say, in this direction. After time t, it is at position s at time t. So s is a function of t. At a slightly later time, t plus epsilon, it is at position s of t plus epsilon. The distance it has traveled in time epsilon is s of t plus epsilon minus s of t divided by epsilon. And now if one takes epsilon going to 0, then this is exactly what we had called s prime of t. But there's another name that we can give to this, and that is the speed. The speed v at time t is the difference in distances that it has traveled. That is to say, this distance minus this distance divided by the time. For example, you could have the distance as a function of time being, let's say, half some constant times t squared plus another constant, let's call it u times t plus maybe another constant c. The way to understand this formula is that at time t equal to 0, the particle was at position c. And now with this formula, we can easily work out what is the derivative ds by dt, or what we could call s prime of t, and that is half a. When you differentiate t squared, you get 2t. When you differentiate u into t, remember that u is some constant, then you get u, and from here you get 0 because the derivative of a constant is 0. And so we get at plus u. That is the speed with which that particle is moving. It's increasing its speed at a rate that's proportional to t itself. Taking the derivative of a function is really an operation. What that means is that imagine there's some kind of a machine. You give it an input, a certain function, and out comes the derivative of that function. There are different ways of writing this, all of which mean the same thing. Sometimes people write it, f of x is put in, the machine is called d by dx, out comes f prime of x. Or some people like to do it a little differently. They say if the function f of x is put in, then df by dx comes out at the point x. Examples. Let's say that you give x squared as the function. Out comes the derivative, which is 2x. Or you give x to the power n, and out comes n times x to the n minus 1. So this machine will act upon this input, whatever it is, f of x, and give you the derivative of that function. In the previous lecture, we learned what a continuous function is. That's a function that's smooth. So if you draw almost anything that you can with a pencil, this curve is going to be smooth. There's a theorem that says a function that is differentiable at the point x has to be continuous at that same point. Now that's very easily proved, because let's remember that the definition of differentiability of a function is that the limit of f of x plus epsilon minus f of x divided by epsilon has to exist. So there is a quantity f prime of x that exists. In other words, this limit as epsilon tends to 0 exists. Let's write this slightly differently. What this says is that f of x plus epsilon minus f of x is equal to epsilon times f prime of x, and now this is some number, some finite number. As epsilon becomes smaller and smaller, what we see is that this right-hand side goes to 0. In other words, f of x plus epsilon approaches f of x. And that's exactly the definition of continuity. Remember that continuity means that if you take any point and you approach it from the left or you approach it from the right, you get to the same limit. So the function coming in from this direction or from this direction leads to exactly the same value. Here's a question. Is a function that is continuous at a point x necessarily differentiable over there? In other words, can every function that is continuous be differentiated? The answer is no. Let's see why. Take this example. F of x is equal to magnitude of x at x equal to 0. Here is the plot of the function. Remember that f of x is x if x is positive. It's minus x if x is negative, which means that it's a straight line going up like this to the right and a straight line going up like this to the left. Of course, it is a continuous function. As you come in from the left, you reach the point 0. As you come in from the right, you reach the point 0 as well. But what about the derivative? Let's see if that exists. What we need, therefore, is the limit of x plus epsilon magnitude minus magnitude of x divided by epsilon. And let's see if this limit exists. Okay, let's begin with x being positive, slightly bigger than 0. In that case, the limit coming in from the right-hand side will be x plus epsilon minus x. So x plus epsilon is positive, x is positive. This difference is written above, the x's cancel, and this is plus 1. This is for x positive. But what about when x is negative? In that case, we will have minus x plus epsilon. So remember that x takes some negative value and epsilon is very, very small compared to x. So this whole thing is negative. Therefore, we've got to have a minus sign over here. And we've got to have a minus, and magnitude of x is minus, of course. So minus of minus x divided by epsilon, which is minus epsilon over epsilon, which is minus 1 for x less than 0. In other words, this limit does not exist. This limit does not exist. As another example, let's take f of x equals x if x is positive and x squared if x is negative. How do we plot this function? Well, to the right it is a straight line with slope 1. To the left it is a parabola that starts off at x equals 0 and goes to the left and increases its value. At x equal to 0, as we come in from the left or we come in from the right, the function reaches the value 0. Hence, it is continuous. But what about the derivative? Let's look at if the limit of f of x plus epsilon minus f of x exists. Does it? Well, let's examine this. From the left, we get x plus epsilon squared minus x squared divided by epsilon, and the result that we get is x squared plus 2 epsilon x. The epsilon squared I'm going to neglect, minus x squared, and we get from here 2x. At x equals to 0, the limit is 0 at x equal to 0. On the other hand, if we come in from the right, the limit is x plus epsilon minus x divided by epsilon, and the result is plus 1 at x equal to 0. So, coming in from the left, we get 0. Coming in from the right, we get plus 1. Hence, this function is not differentiable at the point x equals 0. Of course, it is differentiable at other points. It is differentiable here, or it is differentiable here, but not at this point, even though it is continuous over there. Most functions that one encounters in physics are continuous, and they're also differentiable. But a function like this we just saw is continuous all over here and all over here, but it is not continuous over here. Well, let's take another function which is like this. It's continuous everywhere. Certainly there's no break in the function, but it's not differentiable here, and it's not differentiable here. Now, we can make more edges, and we can keep making these edges like this. So if I look at two edges, it's not differentiable here, not differentiable here. If I can make this distance go down, let's say, as 1 over some large number n, and then I make n very, very large, then this is a function that will be continuous everywhere, but not differentiable anywhere. We've spoken of taking derivatives as being an operation. What that means is the differentiator really is like a machine. It takes the function f and produces the derivative f prime. F prime is also written as df by dx. What if we take the output of the differentiator, that is f prime, and put it through another differentiator that gives the second derivative, f double prime. F double prime is also written usually as d2f by dx squared. So, for example, if I put in the function x squared, the first differentiator gives 2x, the second differentiator makes this just 2. We can continue this process on. Now I'm going to put a third differentiator. The function f produces the derivative f prime. F prime becomes f double prime after it goes through the differentiator. Putting f double prime as the input gives the third derivative, f triple prime, which is written as d3f by dx cubed. So, for example, if I give as input sine x, out comes cosine x, but when you differentiate cosine x, remember you get minus sine x. When you differentiate sine x, again you get cosine x, so out comes minus cosine x. In this lecture, we learned how to take the derivative of a function, what it means, and how to do some simple differentiations. But in order to be able to use it, we shall have to develop this subject more in the next few lectures.